Hello everyone. Today we are presenting our midterm project on content-based image retrieval using color histograms. So this is a group effort by Simone Potluri, Mohit Pedineni, Vasishta Parvataneni, Nagaraj Islawat and Sujan Katkam. We are from Virginia Commonwealth University's Department of Computer Science. So the motivation for this project comes from the challenge of searching and organizing large image collections. Rather than using text or tags, we want to retrieve images based on visual similarity. So that is the central goal of our work. So coming to the background and introduction, the content-based image retrieval or CBIR is a method of retrieving images by analyzing their visual features such as color, texture or shape. This approach contrasts with the traditional methods that rely on manual text annotations. The importance of CBIR is clear in many real-world applications. For example, Google Image Search allows users to upload a photo and find visually similar ones. E-commerce platforms use CBIR to match product photos, and photo organization apps rely on CBIR to group and retrieve images. By focusing on visual features, the CBIR provides a more natural way to search large datasets and often yields more accurate results than relying only on text. Coming to the literature review. In the literature, many approaches to CBIR have been explored. Early methods focused on color histograms. They are simple and computationally efficient, and they work well for capturing global color distributions. However, the limitations is that two very different images can still have similar overall color histograms. Texture features have also been used. So these methods analyze repeated patterns and structures in the image. They often perform better than color alone but require more complex computations. More recently, deep learning approaches using convolutional neural networks have become state of the art. They capture high level semantic features and also can handle very large datasets. However, they are computationally expensive and require large amounts of label training data. In this project, we implement a lightweight CBIR framework based on color histograms. This balances simplicity and also the efficiency while allowing us to clearly demonstrate the concepts. So coming to the method workflow overview. So these are the main steps that include in the workflow. First, we have to import a dataset of 100 images and convert to 6-bit color coding, extract them to the normalized histograms, and then build a db.mat and compare query to target images and then rank them. So this is the overview. So here what happens is each image is processed using a function that is RGB260C, which reduces the color space into the 6-bit representation. Next, we compute a 64-bin normalized histograms using the function getHistCounts. This histogram becomes the feature vector for that image. We then store all these histograms in a matrix called db, which we save as db.mat. This forms the database of image features. When a query image is provided, its histogram is computed in the same way. We then compare the query histogram to every image histogram in the database using Euclidean distance. Finally, the results are ranked and the most visually similar images are displayed. Let's now look at the technical details of our approach. So the 6-bit color coding works by reducing each RGB channel to 2 bits. That means instead of 256 possible ways per channel, we only use 4 levels per channel. This results in 64 possible color codes. So each image is then represented as a 64-bin histogram. To make the histograms comparable regardless of image size, we normalize them by dividing each bin by the total number of the pixels. For similarity, we use Euclidean distance, and this measures the straight line difference between two histograms, and the smaller the distance and the more similar the images. And coming to the Data management, we save the histograms in db.mat and the raw distances in distance.mat, and also the ranked results in ranked distances.mat. This allows us to reuse the results for analysis and also for the visualization without recomputing everything. So these are the results. So these are the results qualitative. Here we show a retrieval example using query image 101.jpg. On the left is the query image. The following images are the top 20 retrieved results based on histogram similarity. We observe that the system performs well in retrieving images with the similar dominant colors. For example, if the query image has large blue areas, the other images with the similar blue distributions are retrieved at the top. However, this also highlights a limitation. A blue sky might retrieve an image of clothing or a building simply because the color distribution is similar, even if the semantic content is very different. So this shows that while histograms are effective at capturing color similarity, they cannot capture higher level meaning or context. In addition to the visual results, we also analyze the quantitative distances. So this table shows the top 10 retrieved results for each image of the 101 .jpg. So this the distances represent Euclidean similarity between the query histogram and also for the each target histogram. So as we see, the closest image has distance 0, which means it is an identical histogram match. The distance gradually increase for lower ranked results. So this confirms that the system ranks images in a meaningful way. Images at the top are more similar to the query than those further down. So although we did not have ground truth labels to compute metrics like precision and recall, this quantitative analysis supports the quantitative results. So this is the demo code walkthrough. So firstly get hist counts.m. So this is for the feature extraction. So this extracts histogram counts from images and converts the raw data into numerical features for the comparison. And secondly, the get distance.m. So this is used for the similarity measure. So here it compares two feature sets and also calculates the distances using the Euclidean distance to see how the similar images they are. And also coming to the build db.m. So this is for the histogram database. This builds a database for all the extractor features and also stores the histograms for a quick search like retrieval. So coming to the main script, the CBIR.m. So here this includes a combination of QBE and also ranking and also the visualization. So here the QBE means it's a query by example, search using an example image, something like that, and also the ranking means it generally results based on the similarity scores, and here and after that it displays the ranked images for visualization. Midterm project repo. The repo includes the data and the source code folders. The data folder includes the import and meta folders. So these are all the extracted images from the import folder, and the meta folder includes all the mat files. So this source code folder includes all the scripts which we are using in this project. Now let's go into the source code. So this includes like all the scripts which we are using till now. So first we'll go into the CBIR.m. Now this is the script. Now let's execute this. We are now selecting 101.jpg. So this is execution. So now the system loads the database of histograms and computes the histogram for the query and compares it with all the images in the dataset and produces the distances. So this is the 101.jpg. and it sorted all the results by similarity and displayed all the query along with the top 20 retrieved images. So these are all the top 20 retrieved images. uh, Now let's see in the variable folder. We can see the ranked results. So in the variable editor, we can also see the ranked results. The first column is the image index and the second column is the distance score. So first we'll go to db builddb.m. So this is what like we use to generate the histogram database. It loops over all the images in the import folder, which applies RGB26cc to reduce their color space, and also extracts the histogram with get hist counts, and also saves the result as db.mat. So this is the result. So this is in the 100 by 64 grid. And now let's go to this rgb26cc.m. This performs the 6-bit conversion by bit shifting the RGB values. This step dramatically reduces the complexity while preserving enough information for the color based retrieval. This function, the get hist counts. So this computes a normalized 64-bin histogram for an image. So this is our feature extraction step, and also it makes all images comparable regardless of resolutions or the dimensions. So now the function get distances.m. So this calculates the Euclidean distance between two histograms, and this is the similarity measure that determines how close or far apart the images are in the feature space. So now this is main script CBIR.m. So this integrates all the components and loads the database, process the queries, and computes the distances, ranks results, etc. uh, Generates both the numeric output and the visualization. Together these scripts form a complete CBIR pipeline. The demo just saw shows an image transformed from raw pixels into a compact feature representation, compared against the database, and finally used to retrieve visually similar results. So coming to the conclusion, to summarize, we successfully built a CBIR framework using color histograms. Our system retrieves images based on visual similarity on color distributions. So the results show that this approach is effective when the color is dominant distinguishing feature. However, we also observed the limitations. The system can retrieve semantically irrelevant images if they share similar colors. The future improvements could include integrating texture features and also the spatial information or deep learning based descriptors. This would also allow the system to capture more complex visual semantics. So, overall, this project demonstrates how classical feature based CBIR can be implemented in a structured and semantic way. So these are the references. Our work builds on several important studies. Swen and Ballard introduced color indexing as an early approach to CBIR. Ruin and colleagues explored relevance feedback to improve retrieval performances. And also, more recent surveys summarize advances in deep learning for image retrieval. These references provide the foundation for our lightweight histogram based system. Thank you very much for your attention. This concludes our presentation, and I would be happy to take any questions. Thank you.